Welcome! In this video, we will find the electric field at distance z above the midpoint of a straight line segment of length 2L that carries a uniform line charge lambda. Alright, so this in red right here is the straight line segment and its length is 2L. Now the first step is always to choose an appropriate coordinate system as we saw in the previous video, and actually I do recommend that you go back and watch example 1 if you haven't, because this is a very similar case to what we had when we had 1 point charge Q here and 1 point charge Q there. So if you're not sure how to solve that case, then this will be even more difficult. So I do recommend that you go back and watch it. Okay, so how do we deal with this problem? As we mentioned, first we set up our coordinate system. That's the first step. So of course the most convenient thing is to set up our 0 right underneath the point of interest, that is above the midpoint of this straight line segment. In this choice of coordinates, then we have one of the endpoints located at point L in the x direction, which is of course a distance L away, and minus L in the negative x direction, which is of course a distance L away as well. And this right here is a distance z away in the z direction. Okay, so that is the geometric basis of what is going on. Now, what is our second step? We have to write down the formula for the electric field. But now notice, of course, that we are not dealing with just point charges anymore. Now we have a distribution of charge. So we have to use the formula that we discussed for the case when we have a charge distribution, which is honestly the exact same thing, except that instead of having simply the charge Q, we have to integrate over our charge distribution. In this case, it is one-dimensional, so we have the charge density, which is this lambda, and then be very careful, because we used to have this r hat vector, and you have to, we will still have it, but be careful, because once we integrate, what we do is that we take every little dl, right? So a little bit of dl here, right? An infinitesimal part of this segment, and we apply this formula, right? So that means that from this point, we will have to find r hat. But then when we take a dl here, thankfully the integral does that for us, but it's important to visualize it, we will have a different r hat. And if we take a dl over here, we will have a different r hat. So my point is that r hat clearly has an implied dependence on where we are on this segment of the line. So that means that you can't just write it outside of the integral, okay? Do not fall for that mistake. If you're unsure, do what I just did, right? Just start checking. What if I move here? What if I move there? And if you see that it's always the same vector, you can maybe take it out. Okay. And then, of course, we still have to integrate over the entire line, which is why we go for dl. And then we divide by the modulus of this vector r hat, squared, of course. And from where we are going to integrate all the way from our left end, which is minus L, all the way to our rightmost end, which is plus L. Okay, what now? Well, what do we do? How do we continue? Well, here is where step 3 comes in. As you can see, these problems are going to be very similar, which is why I like to write this down so that you see that most problems are exactly the same. Now, the next step is to identify the unknowns. So what is it that we know in our formula and what don't we know? So this here is a constant, so check. Lambda is a constant and it is given, so check. Usually you know what the charge density is. I guess in some problems you can try to figure it out, but in this case we can consider that it is known. dl, this is part of the integral, so no need to worry about it. So our problem is once again r hat and the modulus of r. Now we will do the exact same thing as we did before. There are several ways to go about it. Again, teachers usually like to say, okay, if this is vector r, then you call this vector right there like that. You can call it r in this weird way that I can't draw at all. And this thing here is like r prime, and thus our vector is this weird r vector minus r prime, and this is of course correct. But I like to do it considering what the definition of a vector is, right? A vector tells me how do I go from the starting point to the end point, okay? And what I would recommend here is, just to avoid any confusion, don't take the end point. You can of course take it and you will get the exact result, but here you may make the mistake of thinking that the coordinate is L, and that is where mistakes are made. So let's just say that this thing right here is our DL. So we want to go from here all the way to there, right? That's our R vector. So what is this distance? Well, that distance is simply the X value of where we currently are, right? Because we are going to integrate all the way from x equals minus L to x equals L. So this is simply going to tell us where we are, and we will begin at minus L and go all the way to L. Okay, so, and this is why I decided not to place myself on this end, because if you make the mistake of saying, oh, it's simply L, then you are assuming that your vector is not changing. Your vector R does change, right? Because our vector R, if we want to go from here to there, we need to go a distance minus x in the x hat direction, and then we have to go z units in the z hat direction, right? First, we walk from here all the way to 0, which means we have to walk a negative x amount, and then we have to go a z amount in the z direction. Now, does this work for the negative case as well? So let's say that we are here and this is minus 1, right? So that means that this here is minus 1. So we would have to walk how much? Minus 1 in the x direction. So that would mean that if we are at minus 1, then we need to walk 1 in the x direction, right? Because minus, they cancel out. And that makes sense. And maybe we can check this as well. What if we are at x equals 1 instead of minus 1, right? So what if this point right there, this, where x equals 1? Well, in that case, we need to walk minus 1 in the x hat direction, and that also is correct. So there we go. That is how we write down the r hat vector. As you can see, it is the same as in the previous case, in the example 1 in the previous video, except that this time, instead of being L, it is x. Okay, so what is now its magnitude? Well, its magnitude is going to be you can calculate from the Pythagoras theorem, right? Never forget about it. Just go back to the definitions. Don't memorize anything, right? Go back to definitions. Okay, so the Pythagoras theorem tells us that this is this part squared plus this part squared. Do not include the x hat, right? There is a mathematical explanation for that, because the fact that once you square, so x hat squared is 1, and the same goes for z hat. In case you don't know why, that is because x hat, that is a vector. If you are in xyz, it is vector 1, 0, 0. So if you do the dot product between 1, 0, 0 and another vector that is 1, 0, 0, right, you do dot product between these two, and then you get 1, right? Because this times this plus 0 plus times 0 plus 0 times 0. And the exact same thing is true for z and for y also. Okay, that's just a quick reminder. So this is x squared plus z squared. All right. So now the last thing that we need is to actually find r hat, because it is r hat that is in our formula, not r vector. I mean, you could use r vector, right? I like to use r hat, but if you want to use r vector, you can use it, but you have to be very careful. Make sure that you know what it is that you have in your formula and you're actually solving for it. If you write an r hat, you plug in r hat and not r vector. That is a common mistake as well. Okay, so just stick to what you choose. You can use any notation, but stick to it and be very careful. Okay, so r hat is this divided by this, right? The unit vector is that vector divided by its magnitude. So again, I went into more detail in the previous video. So if you are unsure, you should go back to watch it because it sets up the basics for what we are doing here. And we divide by the square root of x squared plus z squared. Okay, so now we have everything we wanted. We have our hat, we have this. Now we have to plug it into our formula. And this is where this sort of problems can be a little bit harder than normal because we will have to integrate. But don't be afraid, integrals are fun, they are your friends. Well, sometimes. Okay, anyways, so let's plug in our hat. So our hat is minus x hat plus z hat, and then we divide by this modulus, and we already have two of those modulus, right? A squared, I mean. So we end up with x squared plus z squared to the 3/2, right? It is this thing cubed. Okay, and of course, all of this we are integrating over dl. Well, what is dl? Well, if we take a look at what's going on here, what we are doing is we are integrating over this line, which goes entirely in the x direction. So a change in L, in where you are in the line, is just a change in where you are in the x direction. Okay, so dl, just to put it clearly, is simply dx. So that's what I just did. Now this integral may look scary. You may be confused as to how you can solve it, but what we have here is the following. So to solve this, first of all, don't panic. This lambda right there is simply the density. It is a quantity. It doesn't change in space. In principle, it could, right? You could find a situation where it does happen, but in this case, it doesn't. It is a constant. So the first thing we can do is simply take it out. So we have lambda over 4 pi epsilon 0. And then we can separate our integral, right? We have one part here and one part here. Now, I'd like to put my positive part first, which is why I will write this as the integral from minus L to L of z hat. Of course, it doesn't matter at all. It's simply, I don't know, I just like doing it this way. Okay, and we divide by x squared plus z squared to the 3/2 power, and then dx. And then, of course, we have the other integral, so minus L to L of x hat dx, and we divide this by x squared plus z squared to the 3/2 power. Okay, so those are the two integrals that we need to solve. We can still actually simplify them a little bit. So we know that z and z hat don't depend on x, right? Z doesn't necessarily change if x changes. So we can factor this out of the integral. So z and z hat. And of course, well, x does depend on x, of course, but x hat doesn't. X hat is simply a constant vector, right? It is a vector, but it is constant. X hat is 1, 0, 0 in 3 dimensions. If you are in 2 dimensions, it's simply 1, 0. So it doesn't depend on x. The direction is always the same. You may be at different points if x changes, but the direction itself, it doesn't change. Okay, so now to solve this, let us call this integral I1 and this integral I2. What I will do now is a very common thing that you do once you have these rather nasty equations. I will simply solve I1 elsewhere and then plug in the result. Okay, so I1 is the integral from minus L to L of dx over x squared plus z squared to the 3/2 power. All right, so how do we solve this? Well, this is a very common integral actually, and it may look nasty, but it's actually a relatively easy integral. Now, the key to solving this is using a substitution. Of course, if this is the first time that you see this, I mean, it's very unlikely that you would have thought of the substitution. Don't worry. But I want to show you the logic behind it. So what we have here is our constant our variable of integration, squared plus something else. The other thing doesn't have to be squared, it can be 1, it doesn't matter. Now, our objective, the logic behind what I will do is that I know that the tangent squared of theta plus 1 is the secant squared of theta. I know that you may be like, wait, why? Why are you even talking about that? It's completely unrelated. That is the logic here. Because if I can turn this into something that is like x squared plus 1, right? Something like that, or maybe like y instead of x, then I could use, okay, let's say x is tangent of theta, and suddenly I have tangent squared of theta plus 1, and this thing is of course to the 3/2, but you know that this thing here is secant squared. So suddenly I now have secant squared of theta to the 3/2, which gives us secant cubed of theta, right? So suddenly you got rid of this nasty sum. So you had 1 over secant cube, which is, you know that secant is 1 over cosine. So 1 over cosine, this is cosine cubed of theta. So suddenly you went from this nasty thing to the cosine. And it turns out that we still have to factor in the dx, which will also help us. So that is just the idea here, okay? I will show you how to do it. But that's just why I want you to know that, actually maybe I won't delete that part. Anytime when you're integrating, or not anytime, but often when you're integrating an integral that doesn't have anything up there, it's simply dx or something, and down here you have x squared plus something to any power. What we'll do here, it works for any power or almost any power. Of course, I don't want to say any single power because there can be a lot of integrals, but this happens very, very often. Okay, so we need to first produce x squared plus 1, so, or something like that. So first, let's factor out of here a z squared. Right, so that is the first step. We simply factor out, so we get x over z, and all of this squared plus 1. And then z, and now we factored out z squared, but then you have to apply this. So we get z squared to the 3/2. So you end up with z cubed. And all of this 3/2. Okay, so basically, since z doesn't depend on x, you can now write down this as 1 over z cubed. Okay, and now we can say, you can either use an intermediate step, but I like to do it like this. Now we say, okay, let the tangent of theta be equal to x over z, right? Because that way, this thing here will be gone. And of course, if we want to apply this, we need to find dx. So this means that x is z times the tangent of theta. So dx is z, which is a constant here, times the derivative of the tangent of theta, which is the secant squared of theta d theta. Okay, if you are unsure how you go from tangent to secant, that is simply the derivative of tangent. You may want to go back and see that because that's a derivative that you will use very often. So it's important that you know it. Okay. So now let's plug it in. So we have 1 over z cubed integral. Now I will not change the limits for now. I will simply leave this undefined. You could change the limits, but I often like to just plug them back at the end, right? Just undo my substitution at the very end, and then I apply the limits. But if you want to do it earlier and you want to change the limits, it's fine. Okay, so dx is z secant squared of theta d theta. And down here we have tangent squared of theta plus 1 to the 3/2. But as we said, tangent squared of theta plus 1 is the secant squared of theta. This is another very important trigonometric identity. Where does it come from? In case you don't recall, this simply comes from the fact that cosine theta squared plus sine squared of theta is equal 1. And if you divide this by let's see, you have to divide by cosine, right? You divide by cosine squared. This is 1. This is tangent squared of theta, and this is 1 over cosine squared, which is secant squared. So that's where it comes from. You divide this by cosine squared. Okay, just in case you didn't remember that. Okay, and now you apply the square root to the secant, right? You get secant, and then you have to cube it. So secant cubed. And then we have secant squared divided by secant cubed. So you end up with simply secant. Now we can take this z outside and we get z squared. And 1 over secant we know is simply cosine. So we end up, after all of this, with cosine theta d theta. And see how our integral has simplified because of the substitution that we used. Okay, and sometimes you will get like cosine squared if this power had been different, or cosine cubed I've even encountered. But then you have to use other trigonometric identities, and the integral will be a little bit harder. Okay, so here we have 1 over z squared, and the integral of cosine is simply sine of theta. But now do not forget that we still need to apply the boundary terms, right? We still have to evaluate the integral. So how do we go from sine of theta, right? How do we undo the substitution? How do we go from sine of theta all the way to x, right? Because what we had was tangent of theta, not sine. And this is where we have to use a little bit of geometry. The fact that tangent of theta is equal to x over z implies that there exists a triangle, a right triangle, where you have an angle theta, and its tangent is x over z. And what is tangent? It is the opposite side divided by the adjacent side. So here, using Pythagoras, we can see that the hypotenuse would be square root of x squared plus z squared. So here, what is the sine of this angle? Well, the sine of theta is the opposite side, x, divided by the hypotenuse, plus z squared. And there it is. So we simply plug this back in, and we get that I1 is 1 over z squared times x over the square root of x squared plus z squared. And now we apply that we have to evaluate between minus L and L. So let's see, this is 1 over z squared times, now the first one, L divided by the square root of L squared plus z squared minus L, right? Now I'm doing this minus L divided by the square root of L squared plus z squared. So minus minus gives us positive, and we end up with a plus here. So we end up with 2 times L. There we go. So now let's plug it back in here. So instead of having this massive integral, we have now found what it is, which is simply 1 over z squared, and then I think it was 2L, right, times 2L divided by the square root of L squared plus z squared. And we have a z here, which will cancel out the exponent, so we end up with 1 over z. And I will just rewrite this there. Okay, so we already found the result for I1. Now it is the turn for I2. Okay, so I2 will fortunately be a little bit easier. So this is integral of minus L to L of x dx, x squared plus z squared, 3 over 2. Now you may be tempted to say, oh, okay, let's use the same substitution, factor out z and use the tangent. But this time we have an x down there, up there. Okay, and the method that I showed you before is valid when we don't have the variable of integration in the numerator. Here, here it is fortunately much easier because we have x squared here and x, which is kind of its derivative, right? If we have x squared and we take the derivative of x squared, we end up with 2x dx. kind of, right? Because it isn't perfectly legal. The way I wrote it, a mathematician would kill me. But the point is that if you derive x squared, you end up with 2x. And while we don't have the 2, we have the x. So what is my point here? My point is that if we use a substitution that involves what is inside of this parentheses, then we will end up with our new differential, right? Maybe dv or something, right? If I say, or u rather, if I say u is x squared plus z squared, then by taking du, I would get 2x, right? This goes away because it doesn't change as x changes. So dx, of course. So x dx is simply du over 2. All right. So that way we can simplify this a lot. So we go, now I won't change the limits of integration. Again, I will, just as I did before, when we are done integrating, I will plug them back in. I'm lazy. Okay, so this is 1/2, y 1/2 from here. So du divided by, and this entire thing is now u to the 3/2. Or we can write this as u to the minus 3/2. And we know how to integrate that, right? That is simply a polynomial. So that is going to be minus, so this would be basically if you derived u to the minus 1/2. So we have to multiply by minus 2. And then you get u to the minus 1/2. Now let's just corroborate this. If I take the derivative, minus 1/2 comes out, they cancel out, and I end up with minus 1/2 minus 1, which is exactly that. Okay, so now we can undo the substitution. So let's undo the substitution and evaluate. So this 2 cancels out with this, so we get minus, and then we have 1 over the square root of x squared plus z squared, and we integrate between so we evaluate between minus L and L. So what do we get here? We get minus 1 over L squared plus z squared minus 1 over L squared plus z squared. And they cancel out and we end up with 0. Now, this is actually something that we could have predicted because our initial integral was an odd function, right? This is even, but this is odd. And we are in a symmetric interval, right? We go from minus L to L. It is symmetric and our function is odd. And odd functions are characterized because if they are above the x-axis, this is kind of siny, if they're above the x-axis in the negative side, then they are underneath on the other side, right? Basically, whatever they have on this side cancels out on this side. So if this point is exactly the same distance away as this point, then they perfectly cancel out. And in our previous case, we got that our result is twice the integral that we got, because that one was actually even in a symmetric interval. So one was above and the other one was exactly the same above as well. So you just added the contribution of them. But it's actually a very good tip. I, of course, wanted to show you how to integrate this in case the limits had been different, right? If the limits were different, it wouldn't have been 0. But it's important to keep an eye. If you see that there is an integral that has a symmetric limits of integration, just quickly check if the integrand is odd, because if it is, then you may save yourself a little bit of work. Okay, so after a little bit of blah blah, this thing here is 0. So our end result is simply this. Now we can perhaps just make this a little bit cleaner. So 1 over 4 pi epsilon 0, and simply rewriting here. And then we have 2 lambda L divided by z square root of L squared plus z squared, and it goes in the z direction. So there we go. That is the electric field that is generated by this line segment. Now here, if you want, you could wonder, well, what would happen if we were to move very, 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 very far away from what we have here, right? Let's say that we go very, 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 very far away, very far away, very far away, as you can see, both points are getting closer and closer together. And if I go far away enough, you cannot distinguish one from the other. So if I'm very, very far away from this configuration, then you would expect that there would be no difference from simply having a point charge that has the entirety of the electric charge. And let's see. If Z ends up being much, much greater than L, let me make some room here, then in that case, what we would have is the following. So 1 over 4 pi epsilon 0 to lambda L. And then underneath we have Z. And look at this. L squared plus Z squared. L is much smaller. So this is basically just Z squared. If you have like a million plus 1, it's basically a million, right? It barely changes. So you can say that it's basically just Z squared. So you have to take the square root of the Z squared, which is simply Z. And then we have this other Z squared. So we get Z squared. And notice that, well, of course, in the Z direction. And then we have this thing. But think of it. We have a line of charge. And then we have lambda is the density that it has, right? It's the density of charge. And it has a length of 2L. So from the definition, what is the charge inside of this? Well, it's going to be the charge density times the length. And that is precisely what we have here. So this is indeed the electric field okay, this is an approximation, by the way, in the case where we are moving very, very, very far away. Now, what happens in another case? Well, what happens if now L is much larger, right? What if L is now like an infinite wire, right? It's ridiculously long. It's now infinite. It is basically infinite with respect to this vertical distance. Well, in that case, let's take a look at this. In that case, we would have 1 over 4 pi epsilon 0 and 2 lambda L in the Z hat direction. And now this time it is the Z squared term that is negligible. So we get Z times L after taking the square root. So the L's cancel out, right? And we end up with this, which is actually, as we'll see, well, later, that is exactly the electric field of an infinite straight wire. So that's kind of nice. You will see that we'll find it via a different method in the future. So yeah, that's just a little bit more to understand what we did. So as you can see, all that we had to do in this problem was that we began, right? We wrote down our electric field. We identified everything that we needed to find. And then we solved the integral. The integrals were a little bit annoying, but the procedure itself wasn't particularly difficult. So there it is. I hope that this video was useful to you, and if it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.